So in the first session in the morning, we showed you some of the topic of the 3 days, HPC. We showed you some of the means we used to teach. And now we're starting into some of the things that are elements of the universe of HPC and Python. And as you have probably seen from the very first presentation from Jan, one of the packages that provide a lot of functionality and performance for not for free, but for very little effort is NumPy. So that is why it is one of the corner pieces and of HPC, in particular if something on a single node is sufficient for you. And I know that many people already here had some exposure to NumPy, not everybody. And for the latter ones, it may serve as an introduction. For those who had some exposure, it may serve as some kind of refreshing the memory or deepening the understanding of NumPy. But first, we should take a step back and ask, well, why is NumPy fast? What is different about NumPy with respect to ordinary Python? And there is a lot. And the first thing is you're probably underutilizing the versatility of Python quite a lot. There's a lot of things you have probably never touched. Who has done self-modifying code? Nobody here. So normally this is something you can do in Python, and it is part of the benefits of an interpreted language, but it's part of the things that don't constrain us too much if we sacrifice it for performance. That's exactly the way that NumPy thinks about Python. It tries to capture the simplicity of the semantics that you can express in code, and it tries to concentrate on a certain subset. Well, as the name NumPy may imply, it's about numerical computing in this case. And it does so by providing you with something that is behind the scenes working in a C library, in a very fast numerical C library, in order to expose calculations that you can access and do from Python in a very easy to understand way. The restrictions here is that you work with numerical data, and in addition, NumPy typically works with a particular data structure I will introduce in a second, and assumes that these types are identical in memory layout. So, and if you have things that fit into that framework, numerical data, more or less all alike, and a lot of those, then I think NumPy can help you a lot. NumPy is an additional package. It doesn't come as a standard module within Python. And maybe there is also a reason for that, because NumPy can be linked to high-performance libraries, linear algebra libraries. So if you have an Intel platform, you may have linked it to some MKL library. If you have an IBM platform, it may be ESSL. Here we are on a Cray platform, and they have their own high-performance math library. And there is a command in NumPy called showconfig, where you can, well, you don't see the entire output, but you will see it in your own NumPy notebook that you will work through in a couple of minutes. And then you will see here, this is on our machines, obviously. No, it's not on our machines. I did it here, but you probably see that the BLAS MKL's info says not available because we are not on an Intel machine. So we'll check for certain linear algebra libraries and report against which libraries this has been compiled. So, and if you see a normal LAPACK library, then maybe that you can complain to your system administrator that it does a relinking of NumPy. So the structure I was talking about, where you hold your numerical data, is called NDARRAY in NumPy. And that is a short for n-dimensional array. So you can have an arbitrary number of dimensions. If you're familiar with pandas, they typically only support 1- and 2-dimensional data. Here you can have 4-, 6-dimensional data if you require that. The memory layout typically is a C array. That's to say the last index is those which is continuous in memory and the fastest in accessing, because you can take these cache lines and use the entire cache line there, as Jan pointed out. And if you don't say anything, it assumes that you want to store doubles, so floating points with 64-bit, 8 bytes. And you can of course, change all these. This is like typical for Python. You have some intelligent defaults that typically work. And if you want something special, you have to specify it. There is one, well, the first line already is an exception to what I just said. So yes, the standard type probably is a float or a double, but if you are generating such an ND array by entering data, the semantics in NumPy says, I will use the data type that takes as less memory as possible, that holds these data without having to do any numerical approximation. So in this case, they are all integer data, and they will use an int64 here. So it's not really the most memory efficient way to do it, but they at least assume all data you will ever enter into that array will be all ints. If this is not true, if this is just pure happenstance that you have some int values at the beginning when you set up this array, then you should explicitly say you want a different type. And you can do so. You see this in here, for example, you specify this with D type, and then you say which D type you want. And there are a lot of those. You can have some convenience functions there when you do arrays, so lots of data, and you want to initialize them to the same values. You can do this, for example, all to 0 or to some sequence of numbers, which you can do by arange here, which only works for int types properly. Don't try to do this for other types. Otherwise, you can use linspace for if you have double or if you have complex data. So like Python, also NumPy can work with complex numbers. You can all put to 1 and then cast to bool, so you will get all true here. And this is something you can check out in the notebook. So there are different ways to start with your ND arrays. And of course, you can also check what's in there. If you get an ND array, for example, as a result, you can check the type of the array. You can check what is the element size in bytes. You can check the shape, which is the number of elements in each of the dimensions you have. So here, if you have a 2 by 3, it will give you the shape as 2, 3. And there are many other ways to do introspection, including getting the address of such things if you're interested in that. The types you have available come in different widths. So you can, if you have really a lot of data and you still want to have them fit in your main memory, or also in your caches, then it maybe is convenient to have to choose a smaller data type if the numbers you're storing fit into such a smaller data type. And you have some special objects where you can do calculation with time. If you have some time series, or if you happen to work in business computing, that may be a little bit more frequent than in scientific computing. You can also work with arbitrary objects, but of course the number of operations you can do on them may be a little bit limited, or you may have to specify them yourselves, which is also possible. So if you're working with complex numbers, you have some of the operations you may want to do on complex numbers only. But for example, the real and imaginary part, they are properties, and they also apply, for example, to an integer array. So you would also find, you can ask the imaginary part of an integer array as well, and it will of course come out to 0. So you have that for all the NumPy. So maybe you're not happy with the type you chose, or which NumPy chose at first, so you can change the type. There is some implicit casting, which you should be aware of. That's to say, as in the beginning, you have an integer array, you put a floating point number, 124.9, into that integer array, you will get 124. It will be truncated. There will be no warnings, no errors, nothing. So you should be aware of that you are here in a subclass of Python that assumes you know what you're doing regarding the types. If you have a list, you can store arbitrary types, and they will come out as you put them in. That is not the case with NumPy, which for performance uses a more uniform layout here. So better explicit than implicit, that is part of the Zen of Python. So explicitly, you can specify a type, you can cast, and you can also do this when you're accessing other data types from Python in order to feed your NDARRAY. So reading has some similarity to Python lists, multidimensional lists, with the exception that as NumPy assumes that you're probably working with dimensions larger than 1, the syntax is a little bit simplified here, so you just have a comma between the different dimensions. Otherwise, the things like the colon or the step, and they all work like in Python lists. So I'm not reiterating that here. Here you see that every second value. However, also due to the fact that they have some uniform memory layout, it is easier to implement something that gives you more versatility in the indexing. It's called fancy indexing, and you can use a list in order to access indices within your NDARRAY. So that's to say, here you are asking for the elements at position 1, 3, and 8. Remember, it's like in Python, the first element is 0. So you're accessing the first, the second, the fourth, and the ninth element. And you see that are the elements here. And if you now are able to specify the indices you are looking for by a condition, then you have the second part here. So here we are looking for all the values that have a modulus 3 of 0, so which are divisible by 0 without remainder. And you can then get exactly those values here. You can have some kind of a true-false mask from somewhere else. And you can apply this. If it has the same length, you can apply it to the array. It will only put out those things where there's a true value in there. And you can generate an index array from these conditions. So it's the same condition we had before. Now we assign it to a variable. And then we can apply it, for example, also to a different array, but in this case to the same array. Here you use it for the same array. Here you see the index array, 0, 3, 6, 9. So, and you get the respective values here. Of course, we can write to our arrays. It more or less follows the same semantics as you would have in multidimensional lists, only you also have to be aware that here the indexing is a little bit compressed. You can not only change the type, you can also change the shape of your arrays. Maybe you have a million numbers that you want to rearrange into something 1,000 by 1,000. So then reshape would be your friend. It may be that you are just want something to iterate through all your data. Although your data, your array is a three-dimensional array. In order to do that, you may use flat, flatten, or revel, depending on the. Then you can use this. These are typically creating views. That's to say, they're not copying the array to something one-dimensional. They're just following a certain indexing within your entire array. And that may make some loops more convenient. Although, as you see, one of the advantages that we will discuss after this slide is that you typically try to avoid loops. So but here you see these are more convenience methods you can use to create arrays. One thing you may have a closer look is on the definition of mesh grid. A, because it isn't that easy to understand. B, because you may need it for some exercises. So getting your data in, well, of course you can type them in, but very often you have your data in some way of files, and then you can generate them, you can load them, you can store them, and NumPy has its own, sometimes also compressed formats in order to load and save such NDARRAYS. So that is typically a much better way than really exporting it as a comma-delimited format or something like that. If you have data that, let me first put a question, who is using regularly data that have more than 10 gigabytes in size? It's quite a percentage, yeah. Typically those things, if you have data that don't fit in memory, well, 10 gig nowadays, of course, fit in memory. Well, a terabyte, only in few places you find nodes that can hold a terabyte of memory. Then there are some structures, like the HDF5 format or some other data analysis packages that may also be worth considering. And Dask, we will briefly introduce you tomorrow or on the third day. HDF5 is a structured format that allows you to read and write in parallel on many nodes in a distributed format. So it uses MPI behind the scenes. So that may be something worth looking into. Other than that, you can have these file accession routines here that will feed your NDARRAYS and that also provide some kind of parsing. So I just said we try to get away from loops. So when you remember the first notebook from Jan, you had a loop where you did your matrix operation and as three loops. And one of the things that makes NumPy particularly fast is that you can have a single operation working on all the elements of your array or a particular dimension of your array, where you don't have to formulate a loop with a single operation. They are called ufuncs, universal functions. And these are all done in C behind the scenes, doing all the necessary performance optimizations you could think of manually, which are not immediately available within ordinary Python. There are, apart from the ordinary operators, addition, multiplication, and the like, you have about 80 different ufuncs, and I've put in a link if you want to have a look on them. So here, that would be the list comprehension here in ordinary Python. Here, just adding up 1 million times, it's 65 milliseconds, which sounds fast. Well, you see, if you're doing it in NumPy, so you have the array and you just add 1 to each of the 1 million elements, you're about 70 times faster. So if you do more operations or more complex operations, 70 times faster may be the difference between a minute and an hour, or an hour and several days. There is one concept in ufuncs you should probably try to grab. That is the broadcasting. So here we are taking the maximum of two arrays which are different in dimension. So we have a two-dimensional array and we have a one-dimensional array here. So the semantics that NumPy is using is it assumes that you have this row here repeated. Yeah, so it will be broadcast to some two-dimensional array where this row is occurring twice, and then it makes sense, and otherwise this one here would raise an error. So you get outputs that have the maximum shape from both inputs. So in this case, this is a larger shape, so the output will have this shape. If you're working along an axis and you do some operations, then it is convenient that you cannot only do an operation on a particular item and each of the operations on a different cell within the item. There may be some operations where you want to add up things along a certain dimension, or you want to have another operation like a moving average or something like that. So, and therefore we have reduction operations, or let's say in this case collective operations that are not all reductions. And there are some examples in the notebook you should really try to understand. Here I think that is easy. You're doing a reduction, and so you apply this by having the operator, in this case addition or multiplication, here it's addition, and then call the respective collective method. So we are adding along the standard array axis, that is 0 in this case, to this array, and then that means we are adding up along the columns here. So you will see some more fancy examples in the notebook for that. We sometimes call these type of operations that work on each element of such an array also as vectorized operations. It doesn't have a direct connection to the vectorization you're talking about in, let's say, if you're talking about hardware vectorization. It means you're applying things for a vector at a time. And there is a vectorize function in NumPy that more or less is is an alias for a Python loop. And as an alias, it also doesn't give you any speed up. So if you want to have a Python function that works on each and every cell of your array, VECTORIZE, when you apply VECTORIZE to that function and then you use that vectorized function on your array, it will do semantically what you want, but it will not provide you with the speed up you are used from the ufuncs that are built in. There is Numba, Jan already introduced that, which also has a vectorized function, which exactly can do that, because it has a compiler, or it uses a compiler. It can provide you almost machine speed for those type of functions you're providing to Numba as a ufunc. Take a very fresh view on NumPy now in the notebook. It's called 02, I think. Probably 02. We are at 02. Introduction to NumPy. Those people who have not used NumPy before, please don't hesitate and ask questions. So we have two people here to help you through it. In our introduction to Python HPC, we typically make a requirement that people have had some exposure to NumPy before. Therefore, this notebook is a little bit more concise than would be typically done for a real introduction into NumPy, but that would require another day of the course here, so we cannot do that. So please ask questions, just point up, and Janne or I will come around and help you.